this video, I'm going to combine the discussion with formal charge with resonance theory. So formal charge provides an electron bookkeeping system for a molecule. It provides a method for keeping track of electrons, but they may or may not correspond to real charges. In most cases, if the Lewis structure shows that an atom has a formal charge, it actually bears at least part of that charge. And this is going to be important for reactivity. So formal charges help us determine which atoms bear most of the charge in a charged molecule, and it also helps to see charged atoms in molecules that are overall neutral. Again, important in determining reactivity. In order to calculate the formal charge, you're going to take the group number, and you're going to subtract the number of non-bonding electrons, and then half the bonding electrons. Let's just apply what we learned. What we're going to do is we're going to use this formula and look at problem 1.17 in the text, which says determine the formal charge of each atom in the molecule. Note that each atom has a filled valence shell. So let's start with the oxygen up here. The group number for oxygen is 6. We are going to say, now the lone pairs are not drawn in, so let me draw them in. We're going to subtract 4 non-bonded electrons minus, now we have to do 1/2 the number of bonded electrons. If we look, there are bonding electrons here, and while that bond is not drawn in, I'll draw it in here. So there are 4 bonding electrons. So that we are going to have 6 minus 4 minus 2. So the formal charge on that oxygen will be 0. Let's look at the nitrogen. First, I'm going to draw the lone pair on the nitrogen. All right, so the group number for nitrogen is 5. There are 2 non-bonding electrons on that nitrogen. Minus 1/2. There are going to be 2 electrons here, 2 here, and here. So 1/2 of 6, because there are 6 bonding electrons. So that we have 5, we have 3 minus 3 equals 0. So there's a formal charge of 0 on that nitrogen. Next, let's look at carbon. Carbon has 4 bonds there. There are no lone pairs. So we have 4 for the group number minus, there are 0 non-bonded electrons minus 1/2 times 2, 4, 6, 8. So that's going to be 4 minus 4, so the charge is going to be 0. Okay. If we do this out for these carbons, I'm going to just expand one of them. All right, we would also see for this carbon here, the group number is 4 minus 0 because there are no lone pairs, minus 1/2 of 8 because you have 4 bonds attached to that carbon, so your formal charge would be 0. So all of the atoms in this molecule have a formal charge of 0. Now we're going to explore a concept known as resonance. The Lewis structures that we've drawn are static pictures of where the valence electrons are present in a molecule. It's important to remember that electrons are dynamic. They are always moving, and they behave as clouds of electron density. These clouds spread themselves throughout the molecule or are delocalized. So electrons like to spread out across a molecule. The more electrons spread out, the more stable the molecule is. And so we're going to use this theory known as resonance theory to describe where the electrons are when you have 2 or more valid Lewis structures. So a resonance structure or resonance contributor is a valid Lewis structure that can be used to represent a molecule. Resonance structures only differ in the placement of valence electrons, not in the connectivity. Okay, so we're going to see it's going to be the placement of valence electrons in a molecule. We are not going to change the connectivity of atoms. Resonance structures are imaginary. Then why are we studying them? Resonance structures represent where the electrons can be, or the probability of electron density. In reality, the electron distribution is a weighted average of all resonance structures. So the true species, the true molecule, is represented by the resonance hybrid. Think about this analogy. Take a nectarine. It has both the properties of a peach and a plum. You can think of the peach and the plum as individual resonance structures, respectively. A nectarine is not sometimes a plum and sometimes a peach. It is always a nectarine. So it's always that resonance hybrid. It's a combination of both. And that's what we're going to do when we draw resonance structures. We're going to show the probability of where the electrons will be located. But the actual molecular structure, the actual distribution of electrons is going to be a hybrid of the resonance structures that we draw. The resonance hybrid will look most like the lowest energy, most stable resonance structure. Now, not all resonance structures are created equal. Sometimes resonance structures can be inequivalent. The more stable the resonance structure, the more it contributes to the resonance hybrid. So what makes a good resonance structure? So a resonance structure is lower in energy or more stable if it has a greater number of atoms having an octet, it has more covalent bonds, and it has fewer atoms having a non-zero formal charge. So when you're drawing resonance structures, the greater contributor to the resonance hybrid will have the greatest number of atoms having an octet, more covalent bonds, and will minimize charges. You need to remember this concept. Resonance provides stabilization. So the more spread out or more delocalized the charges throughout the molecule, the more stable and the lower the energy of the molecule. Electrons that are localized result in a molecule with higher energy and a less stable compound. Resonance stabilization is usually large when your resonance structures are equivalent. Equivalent resonance structures will contribute equally to the hybrid, allowing the electrons the greatest possible delocalization. All else being equal, the greater the number of resonance structures, the greater the resonance stabilization. Let's do some examples to demonstrate these principles. So we're going to work on problem 1.53a, where we have CH3NO2. And we have to draw all resonance contributors for each of the following molecules. And we need to include curved arrows that indicate which pairs of electrons are shifted and going from one resonance structure to the next. So I didn't discuss this in the previous slides. A curved arrow shows the movement of electrons. When you have a curved arrow, okay, the end of the arrow shows where the electrons start. The arrowhead shows where electrons end. So this is going to be the first step in drawing mechanisms. You also have to know that these arrows only show how electrons move. The last thing I want to point out about this arrow is that because there are two hooks on the end, it means two electrons are moving. I'll draw an arrow where you only have one electron moving. So this would be one electron moving because there's one hook on the arrow. So again, these arrows are only showing electrons. So let's start by counting the total number of valence electrons that we would have. Okay, so for carbon, we have one carbon, 4 valence electrons. We have 3 hydrogens times 1. So it's 4, 3. We have 1 nitrogen times 5. That's 5. We have 2 oxygens times 6. So that would be 12. So let's add this up. So we have 7 plus 5. That's 12 plus 12. So we're going to have 24 valence electrons to deal with. All right, let's draw how this is connected. So we are going to have the carbon connected to the nitrogen, and then you're going to have the hydrogens attached to the carbon and the two oxygens attached to the nitrogen. Now, let's try drawing some lone pairs in and do a count because we have everything connected here. So I'm going to put lone pairs so that everything has an octet. Again, practice this skill of drawing Lewis structures. Let's do a count. Let's see. We have 2, 4, 6, 8, 10, 12 bonding electrons, 14, 16, 18, 20, 22, 24, 26. We have too many. All right, so let's make some multiple bonds. All right, so I'm going to take a lone pair off of the oxygen. I'm going to take a lone pair off of that nitrogen and draw in a bond. Now I'm going to count again. So I have 2, 4, 6, 8, 10, 12, 14 bonding electrons, 16, 18, 20, 22, 24. All right, so I'm good. I'm going to just erase those dots. I'm good from the perspective of my Lewis structure is complete. Everything has an octet. Now let's try and draw in those formal charges. Let's start with carbon. All right, so carbon, the group number is 4 minus 0, okay, minus 1/2 times 8 because there are 8 bonding electrons. We're going to see it has a formal charge of 0. You will find that when you see a carbon with 4 single bonds, the formal charge will equal 0. Let's look at this nitrogen next. Okay, so nitrogen is group number 5. There are no lone pairs on that nitrogen. Minus 1/2 the number of bonding electrons, and you can see that there are 8 bonding electrons. So 5 minus 4, we get a 1, and that's a plus 1. So this nitrogen is going to have a formal charge of plus 1. All right, let's do the top oxygen here. All right, so that oxygen has a group number of 6 minus 4 because there are 4 non-bonding electrons minus 1/2 times 4. All right, so because there's 2 bonds, so that's 4 bonding electrons, we are going to get a formal charge of 0 on that oxygen. All right, so again, a rule of thumb, when you see oxygen with 2 bonds and 2 lone pairs, the formal charge is usually 0. Let me come back to this nitrogen. When you see nitrogen with 4 bonds, the formal charge is usually plus 1. If you were to see a nitrogen with 3 bonds and 1 lone pair, the formal charge on that nitrogen would be 0. Let's look at this oxygen out here. The group number is 6. Okay, minus, there are 6 non-bonding electrons minus 1/2 times 2. So this is going to equal 0 minus 1, and you're going to see you have a formal charge of -1 on that oxygen. All right, so we have our Lewis structure, we have our formal charges. Now let's look at resonance. When you're drawing a resonance hybrid, do not change the connectivity. We're only moving electrons, okay? So I'm going to draw my connectivity as I have it above. Now, your book gave you several strategies for moving electrons, right? And when you move electrons, you need to practice this. Right? I'm not going to go through the patterns with you, but I want you to practice it. And we'll practice it in recitation as well. All right, so I put a formal negative charge on the oxygen. I'm going to put a +1 charge here on the nitrogen. All right, so when you're doing resonance structures. You are going to move lone pairs, okay, and multiple bonds. And what I mean by multiple bonds, pi bonds or triple bonds. Okay. So those lone pairs can move between the oxygen and the nitrogen. And then I can take the pi electrons and push them out onto the oxygen. Again, let me explain what these arrows mean. So what the start of this arrow indicates is that the lone pair is going from the oxygen to between the nitrogen and the oxygen. Then this second arrow up top means that this pi bond, the electrons in that pi bond, are moving from between the nitrogen and oxygen out on to the oxygen. Now I'm going to draw a double-headed arrow. This indicates resonance. Okay, this is really important. It's a single line with two arrowheads that indicates resonance. Again, the connectivity is not going to change. So now what I've done is I've taken that extra lone pair of electrons, I've made it into a new pi bond, and then I've pushed a pi bond out onto the oxygen and made a new lone pair. So now I have my two resonance structures. Let's look at them. Okay, so here are my resonance structures. I have the same number of covalent bonds. Everything has an octet. And I have the same number of charges. Now, what I also want to note is that you want to make electronegative atoms negative and more electropositive atoms positive. Okay. All right, so in both structures, I have a negative charge on an oxygen, right? So these structures are equivalent and they contribute equally to the resonance hybrid.